All right. And if you're ready, Jennifer? Yeah, pretty much. So the last speaker in this session will be Jennifer Paykin, who will tell us how to use modal types for the actual quantum programming, I suppose.
Yeah, thank you. So now that we all understand quantum computing very well, I'm keeping things very high level for this talk. So hopefully folks can mostly follow along. But in this talk, I wanted to talk about what I see as one of the core problems in quantum programming language research, which is a trade-off between enabling the sort of high-level, domain-specific programming abstractions that we need for quantum computing, while also preserving properties that are needed to compile that program to quantum devices with very strict resource constraints, which are all of the quantum devices that we currently have and will have for the near future. And so to help manage that trade-off, I'm advocating for the use of modal types, by which I'm referring to the general range of type systems that constrain the way that variables can and can't be used in programs. And so in particular, I'm going to talk about some of the work in progress that I've been investigating as part of the Intel Quantum SDK, which is a C++-based quantum programming framework that is focused on scalability and efficiency for both near-term and far-term devices. But I hope that a lot of these ideas will be applicable to other quantum systems as well. Okay. So what does programming a quantum computer look like? So for the sake of this talk, we should think of a quantum computer as an accelerator, not necessarily used on its own, but used as a component in usually mixed quantum classical algorithms. Classical here is just referring to non-quantum. And so in particular, a programmer will interact with the quantum computer by sending some type of quantum instructions. The quantum computer will execute them and send back probabilistic measurement results in the form of bits or tuples of bits. So today's quantum computers are subject to pretty significant resource constraints. That is partially in terms of the number and connectivity of qubits, the quantum bits available. Things like coherence time, the amount of time that a quantum state will be stable on the quantum computer. And also errors from a variety of physical sources. So quantum computers also operate at near absolute zero temperatures. And as a result, they have very limited access to classical operations. So most of the classical parts of an algorithm have to be performed on a classical computer that is in a place that is maybe relatively close, but is not actually on the quantum device. So the question from a PL standpoint is, well, what are these quantum instructions? And the sort of typical answer today is that these instructions take the form of quantum circuits. These are basically straight line sequences of primitive quantum operations. Those include the unitary transformations that we saw in the last talk, as well as some additional other operations that may be specific to the particular device that you're working on. And so those circuits are either written as a program like this, or they can be described diagrammatically. So to program these circuits, to construct them, many people use circuit generation frameworks, like there's a number of those in Python that are very popular, to explicitly build up those components. And those circuit generation frameworks are very powerful, but they're limited in terms of the expressivity of mixing the classical and quantum algorithms, specifically because the circuit generation frameworks are predicated on the idea that we're constructing a quantum part and the classical parts are managed separately in some way. So some relatively concrete examples of this is using classical if statements and for loops to construct these quantum algorithms, as well as things like classical parameters to quantum gates. So there are some quantum gates that take in classical arguments. So the Intel Quantum SDK, which I mentioned, is an attempt to bridge that gap by allowing writing hybrid classical quantum algorithms in an extension of C++. And the extension has a special type of functions. I know this is too small to read, but it has a special type of function called quantum kernels. And all of the quantum operations occur in quantum kernels, but there can also be classical operations inside those quantum kernels. These quantum kernels are compiled to an extension of LLVM with special quantum basic blocks. And the quantum basic blocks are the equivalent of a single quantum circuit, like we saw on the last slide. There's then a runtime system that dynamically dispatches those blocks, gets back measurement results, dispatches new blocks potentially, and so on. Now, the compiler enforces the property that every quantum kernel, which again can contain both classical and quantum operations, gets compiled to at most one invocation of a quantum basic block. So in general, it'll be compiled to some classical preprocessing, some invoking a quantum basic block, and then some classical postprocessing. And so in order to enforce that, it introduces some guidelines that are, written down in plain English that describe how the classical and quantum data can depend on each other inside of quantum kernels. And so here's the summary, but I'm going to focus in on two of them in particular. So the first rule says that all qubit references must be resolvable at compile time. So current quantum devices don't really have a concept of virtual memory, although that's something very interesting to explore. But so all qubit variables have to be mapped to concrete qubit indices by the compiler. So if we want to still be able to work with qubit variables, as one does in the high-level language, they have to be statically resolvable. So this means we can have qubit arrays like this one, as long as the size is known at compile time, and the indices into those arrays are static. What we cannot do is something like this, where we generate a random index at runtime and then use it to index into the qubit array. Okay. So the second rule says that classical parameters to quantum operations cannot depend on measurement results from the same kernel. So to see what that means, let's consider this quantum kernel, which has a single quantum gate, rot x, which is an x rotation, the rot rotation. That argument takes in that gate takes two arguments, a qubit and a classical parameter theta, which is a double or corresponding to a real number. So in this example, the value of theta depends on a C bit or a classical bit C. This is just a simple, conditional, but this kernel is valid because it can be compiled into two parts. So first, we compute the value of theta on the classical device, and then we execute the rotation, the rot x, on the quantum computer, given that value. But in this second example, instead of being passed in as an argument, the C bit C is first written to by a measurement gate. So the measurement gate is doing measurement, that's a quantum operation, and it writes its value to C. So this kernel is actually impossible to compile to a single quantum basic block because the value of theta can't be computed on the quantum device itself, right? So unfortunately, though, the Intel SDK doesn't currently have a way to check this dependency. So it won't even throw an error, actually. It'll simply behave incorrectly. We just leave it to the programmer to try to avoid this. So, so our goal then is to define some kind of type checker or static analysis pass on the high-level language that enforces the property that every quantum kernel can be compiled to at most 1 QBB. And we want to make sure that the type system is going to enforce all of those English language properties that we saw before. And so to do that, I'm proposing modes. In particular, modes corresponding to the 3 different runtimes that are used in this system. So we have our compile time, we have a classical runtime, and we have a quantum runtime, and the later 2 might go back and forth. So I'll introduce a typing judgment, for now fairly abstract, which says that an expression can be given, is available at mode M, assuming that the variables xi are available at mode M. And to make this more concrete, I'm going to introduce a little toy language of instructions, which has both classical and quantum operations. And the typing judgment, the instructions themselves are all unit typed, but so we just say the instruction is computable at mode M. So to see how this works, let's take a look at a few typing rules. So assignment is fairly straightforward. If both E and X can be are available at mode M, then E can be assigned X. One thing to note is that this is not a binding form. This is assuming X is free in the program. So let's do some quantum operations next. So the rotation gate that we saw before is a special instance of a general unitary, but let's just look at the rotation for this example. So we saw before it takes in 2 arguments, a qubit and, in this case, a real number. So since the qubit variables, we said the qubit arguments all should be resolvable at compile time. So we say that E must have type qubit at mode C, the compile time. And since the real number parameter has to be computed on the classical device potentially, we say that it has to be available at mode R. And if those 2 conditions are satisfied, then the rotation gate can be executed at mode Q at quantum runtime. Okay. So as another example, we have a measurement gate, which also takes 2 arguments, a qubit, which is again should be available at compile time, and a c-bit variable. And since the c-bit variable is being written to by this measurement, it must be available at mode Q. Okay, so these rules do, in fact, enforce the guidelines as expected. So, for example, let's consider the good function that we saw earlier. In the first case, this function is well typed if the qubit argument is available at compile time and the c-bit argument is available at classical runtime. And in that case, theta is also computed at classical runtime, and this can be used as a parameter in the rotation gate. But in the second example, the c-bit variable is not available at classical runtime. It's available at quantum runtime, right? Because it's being written to by the measurement. So therefore, theta is also only available at quantum runtime, and so can't be used as a parameter in the rotation. Now, since the entire algorithm may involve more than one quantum kernel, we also include something I'm calling invoke, which basically promotes the quantum runtime instructions to the classical runtime. That is, it's invoking a quantum kernel. And when it does so, it also promotes all of the arguments, like this c-bit argument here. And in general, like a modal type, we're going to be scaling all of the modalities in the context by that mode. And we can also go in the other direction, sort of demoting or running instructions from higher modes onto lower ones, according to this preorder. So with that in place, we can talk about the compilation from this sort of high-level language into a lower-level runtime language. And this runtime language is much more strictly separating the classical instructions that are executed on the classical device from the quantum basic blocks that are things that are actually executed on the quantum device. So we go from sort of the intuitive separation between classical and quantum runtime to the actual physical separation between classical and quantum runtime. Some differences is that syntactically in these in all of the quantum operations, the qubit arguments are now specifically qubit identifiers, so natural numbers, for example. And the real number arguments to the unitaries, the xi's, now must be single variables, not arbitrary expressions, because those expressions must have been already resolved by the time we call the QBB. The compilation scheme is type-directed in that expressions at compile time can be evaluated at compile time given lowercase gamma, which maps compile time variables to values. Instructions at classical runtime can be compiled to classical instructions, and instructions at quantum runtime are compiled to a triple. It's the pre-processing classical instruction, the QBB being invoked, and the post-processing classical instruction. As a quick example, because I think running low on time, consider our rotation gate. So the qubit argument is going to be can be computed at compile time, right? It will evaluate to a concrete qubit address. And then the rotation gate is going to be first doing the quote-unquote pre-processing of assigning e prime to a fresh variable x, and then inside of the QBB doing the rotation with x. As another example, considering sequencing instructions at quantum runtime. So each individual instruction is compiled to a triple, and then these are interleaved. And so the typing judgments should ensure that the dependencies between these components are not violated. So I said this was work in progress. The soundness is, the correctness of this type system is left for future work. But it should look something like this. We need to define an appropriate notion of equivalence between the high-level and low-level languages. If instructions are available at classical runtime and they evaluate to C instruction, then those two should be equivalent. And then for quantum instructions, if they evaluate to a triple, then the instruction should be equivalent to the expected composition. Okay. So yeah, so to conclude, I'm talking about the trade-offs between these high-level quantum programming abstractions inside of hybrid quantum classical algorithms, and how can we compile those into to near-term quantum computers that have strict resource constraints. And in this particular case, tracking these three modalities can formalize those previously informal rules. And so thank you all for listening.
Thank you very much, Jennifer, for a very interesting talk. Let's take a couple questions and then break for tea.
Do you have plans to put this in? If you plan to implement this in the toolchain, then do you plan to expose these modal types to the users, or do you plan to find some way of trying to infer them?
That is a great question. I think that the
because I tried to figure out something like this for another system, and this was something that came up for me.
So we currently already do sort of a lot of this inference, especially of the compile time versus runtime systems. I think the bigger challenge is going to be I don't want to expose all of these details, but I do want to use them to get useful error messages and integrate that. So I think that's the challenge that I'm anticipating more, but yeah, I think that the inference is also could be quite tricky. Thanks.
I was just wondering, actually, do you mind going back to that slide where you had the example of where it would maybe do something unexpected if you read out a qubit and then use it again in the same block, in the same, like, I forgot the like quantum block thing.
This one?
Yeah. So is this because you're reusing the same actual qubit, or like if you had like a second qubit, for instance, that you could use, like can you like read out half of the system and then continue in the same computation without destroying the other half of the system, like something you would need to do maybe in like teleportation or something like that?
So in this system, the problem is not partial measurement, although you do need to make sure that the quantum device allows for that. The problem is trying to do that all in the same quantum basic block. If you stretch it between two quantum basic blocks, at least in our system, then that's fine. Then that does what you're describing, and it even does this. Those two problems aren't distinguished in that way. The reason why this is a problem is because it can't do this intermediary computation, because we've asserted the fact that every quantum kernel should be executable in at most one quantum basic block. And that's for efficiency reasons, so that programmers know how many invocations of quantum basic blocks they're calling.
Oh, okay. So if you have like multiple quantum basic blocks and you have some just ordinary code in between them, it should like maintain the quantum memory between there, right?
Yes, it should,
Okay.
with the caveat that that's more expensive to do that computation in between. And so if your coherence time isn't long enough,
yeah.
then that state's going to decohere.
Okay.
So it's safer to do it all in one quantum basic block if you can. But that is exactly the reason why we try to maintain that invariant, that one quantum kernel equals one QBB.
Okay.
But yes, we do allow you to write down the programs that do arbitrary computation in between quantum kernels while maintaining the quantum state. It's just whether that's actually being maintained coherently or not.
Okay. That's really cool. Thank you.
Yeah.
All right, I think we'll finish the session at this point then, and let's thank Jennifer again.